Okay, so today's first lecture is to introduce you to Gaussian processes. So if you recall from last time, we looked at this example of a 1000 dimensional multivariate normal distribution. So we talked about how, you might not think about this usually as a living in 1000 dimensions, but this picture here was basically created by adding random normals sequentially, doing a random walk. So taking 1000 steps, each time adding a random normal to the current location. So it's kind of moving around the space and plotting the location at each time from 0 to, or from 1 to 1000. So we discussed how that can be viewed as a 1000 dimensional multivariate normal. So today we're going to talk about Gaussian processes, which are essentially a infinite dimensional or continuous analog of this. So imagine here you've got xt defined for t equals 1 to 1000, but at discrete time points. So you can kind of imagine trying to fill in the gaps between these discrete time points, right? So imagine that instead of having these points here, as we have here, discrete time points, that there was a value of x for every t for t in the continuous space between 1 and 1000. So if you imagine that, that would be a infinite dimensional random variable instead of 1000 dimensional random variable, because the number of time points would be uncountably infinite in that continuum. So that is in essence what a Gaussian process is. It's conceptually a generalization from this kind of 1000 dimensional to an infinite dimensional case, or just think about it as that there's a value of x for every point in time here, not only the discrete times, but the continuous times. Okay, so we never actually observe an infinite number of values. We can't. So the number of observations will be that we'll always observe at discrete time points, or it's also used in spatial context. We'll always have observations at finite numbers of locations in time or space. But the idea is that we might be partially observing a conceptually continuous process. That is, when I say continuous here, I mean a process which is defined at every location. So okay, so on the Dyna list here, the kind of introduction is here, and it starts out by kind of hypothetically thinking about, suppose you want to model the temperature or something else that you might think might be somewhat continuously varying across a space. So just think about, you're in space and you're measuring temperatures at various locations in this space. So we'll just look at a 2D example now to kind of get ideas fixed. So imagine we measured the temperature or some other continuous variable at this point. Let's call it T1. And we'll call the point X1. Okay. Maybe we'll actually call this T of X1. Right. So it's a temperature at location X1. So how might we model T? Well, T is a continuous valued random variable. You could imagine modeling T as a normal distribution, or maybe it would be log normal or something. After a log transformation, it would be normal. But let's just, for now, hypothetically imagine that it would have some univariate normal distribution. So if we now measured the temperature at another location, X2, we would have a second random variable, and we might model that by a normal. But if we wanted to capture the fact that the temperature at X1 and X2 might be correlated with one another, that is, the temperature at one point, if it might be correlated with temperatures at nearby points, then we could imagine modeling Tx1 and Tx2 as a bivariate normal, right? So normal 2 with some mean and some covariance. Okay. So now just imagine adding points, like 3, etc. So you can imagine now you would get a vector of random values tx1, tx2, tx3, etc. You could imagine modeling things as a increasingly high dimensional normal distribution as we add more and more points. But we haven't said, so conceptually the idea is to think that T it kind of exists at every location X in this space. So T of X exists for any X, but we're only measuring it at a finite number of points, say X1 up to Xn. And so the idea of a Gaussian process is that we'd say T is a Gaussian process if whatever points we choose, the joint distribution of Tx1 up to Txn will be multivariate normal. So that's what a Gaussian process is. Conceptually, it's defined everywhere, but whenever we choose a finite set of points, their joint distribution is multivariate normal with the appropriate dimension. So if we go back to the Dynalist and go back to look at this vignette here, essentially the motivation here goes over those ideas. We've got a stochastic process, a stochastic process T is said to be a Gaussian process if Tx1 up to Txr is multivariate normal for all locations x1 up to xr in some space. So often this space will be, if we're in spatial statistics, often that space will be two-dimensional. If we're doing time series, that space might be one-dimensional. If we've got stochastic spatial time series, spatio-temporal, you might have a three-dimensional, two-dimensional space, and one-dimensional is time. But more generally, the space, as we'll see later, the space could be very, very high dimensions in some cases. So the curly X here could be very high dimensions. So there could be an abstract space that these points are sitting in. But for now, concretely, maybe think about two-dimensional space or one-dimensional time or space. Okay, so that's all very well. How are we going to actually work with these Gaussian processes? Well, given that the joint distribution of Tx1 up to Txn, or Txr here, is a multivariate normal, its distribution will be defined by its mean and its variance covariance matrix. So what we need is to be able to specify the mean of T at any given location X. So that's E of Tx, so it's a mu of X here. So think of the mean as varying as a function of location X. And we also need to be able to compute a covariance for any pair of points. So if we can compute the covariance for every pair of points, X1 and X2, then given a finite set of points, X1 up to Xr, we can form the covariance matrix by just computing the covariance for every pair of points. So now this covariance and this mean are both functions of, in the case of the mean, it's a function of location, and in the covariance, it's a function of pairs. Every pair of locations has a covariance. So if we knew those functions, let's just imagine for a moment someone told us what those functions were. Then when you give me some set of x1 up to xn, that's here, I would be able to compute mu of x1 up to mu of xn. And I would be able to compute sigma, where sigma ij is the matrix is just the sigma function applied to xi and xj, right? So if you told me what those functions were, I could apply them to my locations x1 up to xn, and that would give me, my multivariate normal tx1 up to txn would be multivariate normal mu sigma, where mu is given by this and sigma was given by this matrix here. Okay, so if I told you the functions, I could compute the mean and the covariance for any set of points. So Gaussian processes are defined by these functions, essentially, to specify what the Gaussian, so just as you specify a multivariate normal by its mean vector and its covariance matrix, which are finite dimensional objects, you specify a Gaussian process by its mean function and its covariance function, which allows you to compute the mean and the covariance between any pair of points, the mean at any point and the covariance between any pair of points. Okay, so so that's how you would define it, but you need to be a bit careful about, you can't just take any function. Just as you can't just take any covariance matrix for a multivariate normal, the covariance matrix has to satisfy certain assumptions. In particular, it has to be symmetric and positive semi-definite. That is, it's got to have all its eigenvalues non-negative, greater than or equal to 0. Okay, so you can't choose. So actually, the mean's kind of easy, and let's just put that aside for now. In fact, generally speaking, people kind of focus in almost entirely on the covariance when they're working with Gaussian processes, and assume that the mean is constant across space, which might sound a bit weird, but let's leave that for now. We're going to assume that the mean is constant and just look at the covariance. Okay. So specifying a covariance, there's some simplifying assumptions that are usually made when working with Gaussian processes. Not always made, but let's start with these simplifying assumptions, and that is that the process is stationary and isotropic, which means that the covariance between 2 points depends only on the distance between them, right? So the isotropic means it doesn't, if you relax that assumption, it would depend, if it was just stationary but not isotropic, it could depend not only on the distance but the direction between the points, right? So but the isotropic assumption is it doesn't depend which direction you look, going north-south or east-west. The covariance just depends on your distance between the points. Okay, so that simplified things, because now we only have to specify the covariance for any given the distance. How does the covariance function depend on distance? Right, so that's what this this bit here is. A covariance function, maybe I can blow it up, depends only on the distance between the 2 points. That's an assumption. That's the stationary and isotropic assumption. Okay, so now we only have to specify the mean, mu, which is a number, and let's just put that aside for a moment and focus on the covariance, because that's still the harder part. The covariance function, or sometimes called the kernel, k, which is how the covariance declines with distance. So okay, so why would it necessarily decline with distance? Well, generally speaking, in temporal data or spatial data, the closer together points are, the more similar the observations tend to be. So imagine modeling temperature across the Earth's surface. The closer together 2 points are in that geographical space, generally speaking, the more similar you might expect, on average, their temperatures to be. Okay. So that's true for a wide range of spatial and temporal phenomena. So that motivates the idea that maybe the covariance, which is, of course, is like a correlation but unscaled, might decay with distance. So the idea is that we're trying to capture the fact or the notion that things that are close together tend to be more similar, things that are further apart tend to be less similar. And so here are 3 examples of covariance kernels. The squared exponential here, the Ornstein-Uhlenbeck, and the Matern, whose functional form's a bit complicated, so I haven't written it down, but we'll see a picture of what kinds of patterns it produces later. And it's widely used in geostatistics. It comes from the geostatistics literature. So here are 3 different functions that guarantee, so maybe I should say the squared exponential just decays exponentially with the square of the distance, and the Ornstein-Uhlenbeck kernel, it decays with just the distance, the exponential of the distance rather. So So these are three kernels. They all will give you positive definite or positive semi-definite covariance matrices if you use these. They're guaranteed. Okay. So what do these different kernels look like, and how can we understand the Gaussian process in a bit more concretely? So again, as usual, I encourage you to think about simulating what a Gaussian process might look like. So this is what we do here. We take the squared exponential kernel as an example. And so here, what I do is take the 100, I take X, the locations, to be just 100 random locations in the space between 0 and 1. And I essentially generate what the Gaussian process's values are at those locations. Okay. So I'm just creating one realization of this Gaussian process. And actually, I'm obviously only generating it at a finite set of points, but conceptually it's defined everywhere, and I can ask questions like, well, what's the value of the process given that I've seen it at these 100 points? What's the value of the process at points in between? I can ask that kind of question because it conceptually has a value at every location. So we'll come back to that idea later. Okay, but for now, let's look at the simulation. So this line here, I compute the distance matrix, and the covariance has a length scale associated, which says essentially how fast does covariance decay with distance. And then this is the squared exponential kernel. And then, of course, having computed the covariance matrix, here I've assumed mu is 0. So I just generate y to be a multivariate normal. There's this 1 means I just generate one value. Its mean is 0, and its variance covariance matrix is this sigma SE. SE stands for squared exponential. And then I just plot y as a function of x, and that's what it looks like. So you can kind of see that it's a pretty kind of smooth curve. You see that points that are nearby one another tend to be closer in y space. Points that are near to one another in x space tend to be closer in y space than points that are further away. And you can also kind of guess that, like, if I asked you, well, what's the value of the process? Would you guess for the value of the process at x equals 0.4? Given these data, you would kind of be able to fill in the gap and have a pretty good guess of what y was at x equals 0.4 based on these kind of data. Okay, so that's just one realization. So, let's generate a bunch. So here's 9 different realizations of a Gaussian process whose covariance is given by that squared exponential kernel. What you can see is that these are pretty smooth curves. So that's because of, that's not to do with being a Gaussian process, it's to do with that specific kernel. The squared exponential kernel tends to give very smooth curves, and you can actually study mathematically things like how differentiable, how continuous are these are the curves that are generated by these kinds of random process. Much smoother than the Brownian motion kind of curve we saw earlier, which is more like, well, very closely connected, in fact, to the Ornstein-Uhlenbeck covariance kernel that we'll see in a minute. Okay, so you see these are 9 different realizations from the Gaussian process. You can make the length scale affects how quickly things change with space. So we had a length scale there I mentioned controls how the covariance declines with distance. So if we change that length scale parameter, we get things that change more quickly, as here, but they're still pretty smooth, as you can see. Or at least you can kind of guess that obviously we haven't actually got the continuous values here. We're interpolating from the discrete ones, but you can kind of visually see they're pretty smooth. If you use a different one, like instead of the squared exponential, just the exponential or the Ornstein-Uhlenbeck. So actually this tends to produce things that look like Brownian motion, because it's kind of a modified Brownian motion where the modification tends to pull things back towards 0, because Brownian motion, if you just keep running it, will kind of float off further and further from 0. So you can just add a kind of a term that tends to bring it back towards 0 to counteract that tendency to disappear off, and you get the Ornstein-Uhlenbeck process, which is a Gaussian process with an Ornstein-Uhlenbeck covariance kernel. And if you look at the pictures, you can see they look kind of quite a bit rougher than they're changing kind of a bit more suddenly and than the squared exponential kernel. Okay. So, depending on what things you're modeling, what the features are of the things you're modeling, you might choose one of these kernels or the other, right? If you think things could vary pretty dramatically suddenly over a short distance, you might be more inclined to go with the Ornstein-Uhlenbeck. If you're thinking about things that are much smoother, you could have a squared exponential. And actually the Matern tends to produce things somewhere in between. It's like kind of a bit smoother than the Ornstein-Uhlenbeck, but a lot less smooth than the squared exponential kernel. So the covariance kernel affects how it affects the covariance structure, the correlation structure, which you can think of as affecting, what do these curves look like. And I've plotted all these in one dimension just because it's much easier to visualize things in one dimension, but you could imagine, maybe in your head, think about doing this in 2 dimensions. You would have a similar thing where points that are further apart tend to be more similar, and you've got a surface in 2 dimensions. That's what the Gaussian process is. And if you just look at a finite number of points in that surface, you get a multivariate normal where points that are close together tend to be more similar. And exactly how rough or smooth that surface is depends on the covariance kernel, or how rough or smooth it is, at least in expectation, or well, typically smooth it is depends on that covariance kernel. Okay, so I think that's the end of that introduction to Gaussian processes. Have a look at the vignette and make sure you're comfortable with this idea that there's conceptually an infinite dimensional random variable, but you're only observing it at a finite number of points. Okay. Maybe I can say one more thing, which is about the interpolation. So let's go back to this example here where, imagine I asked you to interpolate point 4. So we can use the ideas we learned last time about precision matrices and conditional distributions to compute the conditional expectation of t.4 or y at x equals 0.4 given all the other data. If you think about it, these were 100 points. If I add another one, I've got 101. So if I add 0.4 into the mix, I now have a 101 dimensional multivariate normal. And so I can compute the conditional expectation of that 101th point given all the others by forming the 101 by 101 precision matrix, just as we saw in our example last time. And so that process of kind of estimating the conditional expectation of the process at some unobserved value given the observations at other locations is called Kriging. It comes from the geostatistics literature. So if you see the word Kriging, it means it's the idea of kind of filling in gaps here in given observed data. And you can see how essentially this kind of these Gaussian processes could immediately be used to interpolate surfaces or in 1 dimension, 2 dimensions, or indeed in any number of dimensions. So that's one application for you.